So part A has an average of 90%. That means that mastery in the class looked like getting an A minus. I think we can go up from there, and I think that we can get higher than a 90%. My OCHEM 1 averaged on part A 93%, is technically the cutoff for an A. So that's where I'm going to encourage you guys to do. But you know that it doesn't just depend on you, right? It's your classmates that do that. So you've got to collaborate, get to know each other, study together, work together, so that you can bring your class average up. 87% average for the part B, which is 3 points higher than my OCHEM 1 part B average. And you guys had to do 2 mechanisms and predict a resonance structure. You can see on part A the low score was a 60, but on part B, actually the low score was a 0. So that means the mechanisms didn't have anything correct, and the resonance did not model what a resonance structure would be at all, broke too many rules. So I want to point this out because mechanisms are a big part of our class this semester. And a number of you were able to use the notes that we had in your prior knowledge to do really well on the unit test here. And some of you are not quite there yet. Mechanisms is a big part. It'll always be on the midterm. It'll always be on the final. It will be on most of the unit tests. And so I do want to make sure that we're all doing as well as we can on mechanisms all semester long, in addition to all these other things. All right, so section 15. Actually, I want to point out one thing before we dive into it. You have a analysis of an organic compound assignment coming up September 24th, which I think is next week, next Wednesday. And I want you to look at what it is. IR predictions. Maybe it would have been better for me to have this due before our first unit test, since there were potentially questions on IR. I actually decided last minute, like Wednesday night at literally 10 p.m., I was finishing your unit test. Don't be like me. And I decided last minute that I was not going to have a question on NMR, a question on mass spec, and a question on IR, but a question on spectroscopy. And so that was one of the biggest banks of questions. So some of you may have gotten NMR both attempts, IR both attempts. I don't know that there were actually any questions on mass spec because it's just not something we're going to use much. But IR and NMR are very useful things. IR especially to me. So your next activity is to apply IR to your compound. That's not going to have anything to do with our learning objectives in this unit. But I want you to be aware of it so that you can lean into it, yeah? Okay? And before I show you the next file that I want to point out, I want to remind you of where we are in the class. Today is the last day to drop, so if you were unhappy with your unit test score, or if you realized I do not have the time to take this many unit tests all semester long, if this is what they're going to be like, I encourage you to reach out to me and let me know. Today is that last day to make a decision. So hopefully you've been thinking about it. But we've got 3 weeks in this unit, and then 3 weeks in the next unit before our midterm. You'll notice that 2 weeks in the next unit, and we lose a day for fall break. My goal is not to spend all of our 3 weeks here. My goal is to spend 2 and maybe a half weeks here and get a head start on Unit 3 a little bit early. The nice thing is that Unit 3 it has no mechanisms. but it's heavy on multi-step synthesis. So there's a lot of review reactions in Unit 3. There's some new reactions. But because of that, we don't spend a ton of time on it. So it's our smaller unit. All right. Then, I wanted to point out this molecule that I uploaded literally 20 minutes before class. I'm just going to pat myself on the back a little bit. I'm surprised I finished grading all of your unit tests, and I made this before class started after like 3:40. It was not easy, but it was really helpful that you guys did well on the unit tests. It cut down on how long it took me to grade. Okay. Oh no, this is the wrong document. Please tell me I'm just in the wrong unit. Oh, thank God. You wouldn't believe how many times I upload the wrong document. Actually, a lot of you would believe it because you've had me before. These are our two units, our two sections in this unit, benzene and aromaticity. These are your learning objectives. Again, I've highlighted kind of the key words, the ideas, basically what I think of when I write a unit test question. Unit 16 looks like a lot, but it's just a lot of reactions. And I want you to notice you're actually only learning 2 types of reactions in section 16, just a few different flavors of those 2 types. I am thinking about this now. Number 6 in section 15 is also talking about reactions, and I think that what I'll do is add to this, like I did below, and actually name all of the reactions that I expect you to know. Was that helpful in the OCHEM 1 review learning objectives to have the list of all the reactions? Yeah. Okay, great. That's something I'm going to add then underneath section 6, so you can think about that. I'm going to be adding that. All right, are you ready? Let's do it. Benzene is an interesting molecule. I was just talking with my OCHEM 1 class last night about how benzene is not an alkene. Why would you suspect that benzene is an alkene? Carbon-carbon double bonds.
I was going to ask, did we cover anything about Diels Alder and the M-theory behind that at all? Or are we going to?
No, but actually, you remember lab from summer. The lab actually talks more about the MO theory of the Diels Alder reaction, which is that the pi bonds of the diene and the dienophile overlap in stabilizing ways or not stabilizing ways, but not destabilizing ways.
So are we going to go over it all, anything like that?
We're going to talk about the MO theory of benzene and other aromatic compounds. One of our learning objectives, number 5, evaluate the energy of molecular orbitals for aromatic compounds and conjugated systems.
I'm just thinking of the...
Now that I've said that, I think I need to add a learning objective about frost circles, because I often ask about frost circles.
I'm just kind of thinking about the HOMO and the LUMO of the dienophile and the diene. Oh. And how those can sync up versus not syncing up.
I don't think we need to know that. I just think you taught us that.
Tell me again what your concern is about the HOMO and the LUMO?
How you have your diene and your dienophile. If the HOMO of the diene and the LUMO dienophile are in phase or out of phase, it will determine whether or not a bond or not to become a Diels Alder.
That's true.
Are you sure that?
No.
Okay.
Because it doesn't, I mean, that's just like true of all reactions, not Diels Alder. If you have SN2, then the HOMO of the nucleophile needs to be in phase with the LUMO of the electrophile. Otherwise, those orbitals can't overlap and you can't create a bond and break the bond. And orbitals being in phase is kind of strange, right? Because how do you decide when you're drawing a p orbital whether the top is shaded or unshaded? And what does that shading and unshading mean again?
Negatives in front of the wave function.
It's describing the math. That's it. So is the shaded a positive in front of the math equation, or is it negative? I don't know. I don't care. I don't think it really matters until you get into that field, which is why I don't care. So when you're drawing an orbital, if you put another orbital next to it that needs to go through a reaction together and they're out of phase, then just draw it differently so that it's in phase. But there is something to be said about why the HOMO of one reactant might not be able to react with the LUMO of another reactant if, no matter how you shade their orbitals, there is not good overlap. And I can briefly say, if you have a pi bond like this, and then you try to attack it, or have it attack, rather, a pi bond that looks like this, nothing will happen. It doesn't matter how you flip the shading of these orbitals, there will never be constructive overlap. So those two orbitals cannot cause a reaction. And the Diels-Alder is interesting because it's not just a nucleophile and an electrophile. It's not one HOMO and one LUMO. It's two HOMOs reacting with two LUMOs. The HOMO of the dienophile attacks the LUMO of the diene, and the LUMO of the diene attacks the LUMO of the dienophile. Cyclic. They attack each other. So you've actually got to consider two sets of orbitals and how their phases overlap. I gave you an example of this when I showed you, what was it? In the first week or second week, I showed you the orbitals involved in the formation of the halonium ring. You are using the pi bond of the alkene in order to break the sigma star bond of the bromine, and additionally, you're using a p orbital with a lone pair on bromine to break the pi antibonds of the alkene. It's two sets of orbitals. Cyclic. It's a cyclic reaction. 3 arrows all at once. Does that make sense?
Yeah.
Does that answer your question?
Yes.
Can I go back to talking about benzene?
Only if you want.
You guys want? Can you name this compound for me? Cyclohexene. Do you agree?
Z.
There is no E. It's too energetically strained. Can you name this compound for me?
1,3-cyclohexadiene.
Good. 1,3-cyclohexadiene. 1, 2, 3. Alkene starts on 1. Alkene starts on 3. Someone other than those two, can you name this compound for me? 1,4-cyclohex. Sorry, I didn't mean to cut you off.
No, you did.
Keep going.
Cyclohexadiene.
Good. 1,4-cyclohexadiene. She said, no, you did. Can you name that compound? Why is it not 1,3,5-cyclohexatriene? What'd you say? Ring to it? No, you're all wrong.
Because they're all the same.
What are all the same?
It doesn't matter which one you started at.
It doesn't matter where you start, and so you could just call it cyclohexatriene.
Mhm.
Okay. Why don't we call it cyclohexatriene? Why do we call it benzene?
Do you know what? Does Benz mean anything?
Yes, the name benzene does have a meaning. I don't remember it. I don't think so. But there's an interesting part of the name benzene. What does it sound like it contains by having that suffix? It's not an alkene, but it's named like it has an alkene. The one thing I do remember about benzene's name is that as a substituent, it's called phenyl.
Mm-hmm.
And that comes from meaning the thing that brings light, something like that. But this is not 1,3,5-cyclohexatriene because it does not give characteristic alkene properties. I want to derivatize these a little bit. And let's review some important alkyl nomenclature. You know what? I may make some changes to some of these. It'll make it more useful. Can you name this? Raise your hands. Jacob?
1-methyl hexene.
You forgot the ring? Sorry?
Cyclohexene.
Good. Oh, I put a Y in a weird spot. 1-methyl cyclohexene. Why did you choose 1?
Because the alkene and the methyl group are on the same carbon.
They can start on the same carbon. It can't be 2-methyl cyclohexene because that maximizes the locant. Instead, we can minimize the locant by calling this 1 and numbering this way. Can you name this structure? I want you guys to think about it for a little bit more before you answer. What is the name of that substituent, first of all? Do you guys want to help? Isopropyl or butyl?
Isopropyl.
Isopropyl, you got it. What do you prioritize? The locant of isopropyl or the locant of the alkenes? Which alkene? Both alkenes. Prioritize the alkenes above the alkyl. So where should you start such that you prioritize the alkenes and give the lowest locant for isopropyl?
From the clock.
Left and go clockwise. Because otherwise your choice is to go here and go counterclockwise, and isopropyl is at 6. So what's our name?
1, 3, or 5 isopropyl 1, 3 diene, or cyclo 1, 3 diene.
Good. 5 isopropyl. Why did I put methyl? Because I'm not thinking right. 5 isopropyl, 1,3-cyclohexadiene. You agree? Prioritize the alkenes, then prioritize the alkyl. Can you name the last structure? Do you know the substituent name?
Isobutyl.
Not isobutyl.
Oh,
Tert-butyl. Just for reference, isobutyl is this guy, where it looks like an isopropyl group, one carbon off.
Yeah.
Tert-butyl, because we've got that tertiary carbon. Okay, that's a quaternary carbon, but imagine that you cut it off. What is it? A tertiary carbon connected to a carbon chain. It's a bad name. How do we minimize locants here?
You do the alkenes 1 and 4.
Okay, start here and go this way, or start here and go this way. You want to say it?
Sorry, you can just do it back.
Oh, okay.
This way to minimize the number. And I'm terrible at clockwise.
Yeah, that's fair.
Just draw a rainbow.
Oh, you know, I think earlier I said counterclockwise. Oh, that is counterclockwise. Yeah, no, it's hard. I know. But I told you guys, if you sit as the clock numbers, the clock moves counterclockwise. So that's not really fair. Is it clockwise as you see it or clockwise as the clock sees it? You know? That's what I'm saying too.
Keeps me up at night.
You know what direction hurricanes rotate? Depends on which hemisphere you're in. They say the northern hemisphere rotates one way, the southern hemisphere rotates the other. But are we talking about from the sky or from the ocean? Because it's a different direction. You're right. And the same with tornadoes. They rotate one direction in the northern and southern hemispheres, opposite directions in the different hemispheres, but I couldn't. You know, they say it's this way, but I don't know what their perspective is. Anyways, Jamie, what is it?
Clockwise.
Good. So, the locant position for tert-butyl. 1, 2, 3. 3 tert-butyl. 1 for cyclohexadiene. I don't want to call it that. You want to call it that. So that you get the points on the exam. All right, now, riddle me this. If benzene was a cyclohexene, I want you guys to take 2 minutes and write down the names of these, or really just the prefix, assuming that the suffix is cyclohexatriene. Okay?
Assume it's cyclohexatriene.
Assume that this is not benzene. Assume that you are an 18th century student and benzene has not been named yet. And you are trying to name this structure. Follow the rules that we've just been talking about. How would you name these two? If anything, just focus on the prefix you would give it to describe the placement of the methyl groups. Benzoin is not benzene. Benzoin is a different compound.
Benzoin. Wait. It says it's from there. Which is from benzoin.
Oh.
It goes like this, and then eventually Faraday has something to do with it. Oh. It doesn't say.
Okay.
Apparently,
But
apparently, Lubenjawi.
Lubenjawi. Benzene. Yeah.
Benjawi?
Somehow that became benzene.
Benjawi?
My little brother wanted me to ask you a question. He's,
Jackson.
no, my little brother.
Oh.
My older brother.
Oh, I can't.
He wanted me. He said you're taking chemistry right out of the ask your professor why adding phosphates helps something lock in liquid when you're cooking. My understanding was the waters will orient themselves to lock on to the main charge of the phosphate.
Hydrate the phosphate. Yeah, that's what I would say too.
Like it would take a lot of those waters to lock onto it.
One thing about adding salts or really any impurity to a liquid is that it increases its boiling point, and that's because it now requires more energy to get that compound away from the other compounds. And so yeah, I would imagine it would hold on to the waters better. And I don't know what it means, lock onto. Are we baking? Are we cooking?
He's keeping his pasta dough hydrated.
Okay. Yeah.
Great.
So while it's like in the oven,
While
rising, or while it's covered, rising.
While he's storing it.
That makes sense then. Yeah.
My explanation?
It's just not gonna. Yeah.
I told him like the same way when you dissolve salt in water, the oxygens orient to the positive sodium ion.
Yeah.
And the other way around.
Totally.
Yeah.
I can see it. And phosphates are inherently good for you, so it'd be better than adding something like a sulfate, which I don't think you necessarily want to take in. All right, what did you come up with? The prefix for this one. Good. You would say 1,2-dimethyl cyclohexatriene, or 1,3,5 if you weren't convinced that you can't change the alkenes, hexatriene. And what would you call this?
You have to count through the alkenes, so it's 2, 3, right?
Did anybody else come up with something other than 2, 3? I'm putting this in red because it's wrong. Why? Cordelia, you got the same?
It has to start on one of the alkenes and follow that direction.
That's correct. It has to start on one of the alkenes, but they're saying it started on this alkene. 1, 2, 3. Do you agree? You're saying it started here and went all the way around, or here and went all the way around. But theirs is also starting at the start of an alkene, right? Do you want to add more?
If you're going that way, that 2 is starting on the back end of that.
No, I'm counting through it. I'm just like here, it's 1, 2 going around, counting through the alkene. This is 1, 2 counting through the alkene.
But if that's 2, 3, you're counting the back side of the alkene rather than start counting in the front of the alkene, going that direction.
It's not. I think what you're saying is like if I started here and did 1, 2, that would be wrong
Yeah, that doesn't make sense.
because I'm not counting through the alkene. But I don't have to. I mean, I could have started here. Would you guys agree? I could have said 1, 2, 3, 4, 5, 6. It's just where the methyl groups are ending up. That's all. So it's not inherently wrong because the methyl group is on the second carbon of the alkene. It was on the second carbon of the alkene here too. Alkene, sorry. Do you want to add anything to it, Cordelia?
I just thought my only thought is that it's because the methyl and the alkene will start at 1, so it's the lowest locant for both of them.
That's it.
The 6 is higher.
You're looking for the lowest locant set possible. And there are 2 locant sets, which is 2,3-dimethyl, and that was the one I was thinking you guys would all walk into. And then there is 1,6-dimethyl, and I actually need to clarify something. It is not the lowest locant set possible, like I just said. It is the lowest locant set at the first point of difference. 1 is smaller than 2, despite the fact that 6 is larger than 3. I'm peer reviewing a textbook for someone I met at a conference, giving critiques on it. And in the chapter on nomenclature, they say you should add up the sum of all your locants and look at the total, because the lowest locant total is usually the best one. And then 2 examples in, they go, and by the way, here, the sum of the total locants is bigger for the wrong answer. So you should go with the first difference. So what my comment was don't tell them to sum them up if it's not going to work. Imagine if you did that here. 2 and 3, 5, 1 and 6, 7. It's not the lowest locant set sum. It's the lowest locant set at first point of difference. So we actually number it from here going around in order to get that lowest locant set. Now, what would you call these two structures based on their names? What is their relationship? You would call them structural isomers. What do structural isomers have in common? Chemical formula. Do they always share the same functional groups? They don't have to. Which means they don't always have the same chemical properties. These would have generally the same chemical properties. Do they always have the same physical properties? No, oftentimes those structural isomers have different boiling points, different melting points, different polarities sometimes, which means that they can often be separated. And this is one of the reasons that people started realizing cyclohexatriene doesn't exist. It's because these proposed structural isomers cannot be separated. They're not structural isomers. These are resonance forms of the same compound.
Because they can't be isolated?
They also have the exact same reactivity. There is no 1,2-dimethyl 1,3,5-cyclohexatriene. And there is no 1,6-dimethyl cyclohexatriene. There is only 1,2-dimethyl benzene. And so the advent of this circle came about. When it is okay. In section 16, we're going to start looking at reactions that utilize the aromatic pi electrons as nucleophiles, or break the aromatic pi electrons as an electrophile. You cannot show that attacking or breaking of the pi bonds from the circle. Can somebody tell me, just by looking at that structure on the right, how many pi electrons are in that structure? You got that from the structure on the right? From the circle? How would you know that this circle has 6 pi electrons?
The textbook has told us that's what that's saying. We all just do.
The circle implies 3 pi bonds.
In this case, it does. But we can use this circle on other structures as well, and it doesn't always mean 6 pi electrons.
Could you give an example of another structure? 'Cause I don't understand.
We're going to get into it. Number 2, evaluate aromatic, anti-aromatic, and non-aromatic character in compounds. That is where we're going to look at different cyclic structures that have this overarching aromatic character. We're going to define what aromatic means. So I do want to just preface, this is risky and wrong, but it's just so convenient. So I have no qualms about you using it, but you must use the 3 double bonds in reaction steps where those electrons are needed. You cannot assume them otherwise. Do you have a question, Cooper?
I was going to say, when you have the circle, you can, you have some assumed hydrogens, but you can kind of assume, if you think about it, as, 2 hydrogens per normal cyclohexane ring, you could just say the ring means, you can kind of deduce from that.
Yeah, actually you're right. You know how many hydrogens are here.
You kind of think of the ring means there's no hydrogens in the middle, and then that will help you figure that out.
You also know that there are no charges. How do you know there's no charges on this structure? Good. Charges have to be explicitly shown, and there are none. So what's the only way that each carbon can have just one hydrogen and kind of participate in this pi bonding without any charges? Is if it looks like this. So if I gave you this, and you drew this instead, are you wrong? If I gave you this, and you drew this instead, are you wrong? No. You're just drawing a different resonance form. And I want to make it clear, in section 16, we're going to do a lot of reactions. I think that I instinctively draw my pi bonds in a specific way. I don't think about it often. And then somebody looks at their notes and they're like, oh, I got it wrong. Like, why? It's exactly right. And they're like, my pi bonds are in the wrong spot. Or they look at my answer key compared to their test, and they're like, I must have lost points because my pi bonds are in the wrong spot. Resonance forms that are completely equivalent because neither of them is actually correct. Yeah? I want to get more into MO theory around these pi bonds and the definition of aromatic. But first, I want to go into some terminology and nomenclature around aromatic compounds. When we talk about a benzene being substituted, we're talking about hydrogens being replaced by something else. Can someone tell me if the structure on the left is substituted? Is it a substituted benzene? What label would you put on the degree of substitution for that benzene? Di-substituted. Two substituents coming off of it. I actually had this as a test question once. This was the product of a reaction maybe, and one of the multiple choice questions was the compound shown is mono, di, tri, or none of the above. And they said none of the above because it comes back around. And I was like, no, definitely di-substituted. Two of the carbons of benzene are substituted. It doesn't matter if something loops back around or not. Two of the carbons of benzene are substituted. What would you call this?
Tri-substituted.
Tri-substituted.
Is the word ketone ever used, like the actual like KET ever used in that nomenclature?
In the name of a reaction, there's a reaction called, there's a functional group called a ketal. But IUPAC is trying to push for people to call it ketals. But at the moment, it's grouped under acetal, which incorporates aldehyde precursors and ketone precursors. They're trying to make aldehyde precursors acetals and ketone precursors ketals, which is funny because etymologically, by looking at the nature of the word, I think acetal is derived from aldehyde at the end. Ketal then is like ketone aldehyde, which doesn't make any sense.
That's how I thought you, when you were saying that's how I thought you meant aldehyde. Just bearing the word ketal.
Yeah. I think it's funny that they're trying to push for that. Okay, so that's what we're looking at with substitutions. You can have benzene, mono-substituted benzene, di-substituted benzene, tri-substituted benzene, it goes on, but to be honest, we don't talk about it much. And then there are 2 carbon positions that I want us to look at. This position, just off of benzene, is called benzylic. Which is unfortunate because it is not a benzene carbon. These carbons that are on benzene are called aryl. Because it's aromatic. So kind of like alkyl, this is aryl. The ring itself can be abbreviated as phenyl. Yeah?
So when we used to talk about anti-aromatic and non-aromatic, are they still aryl if they're in a ring-like structure? Or does it have to be an aromatic ring?
One more time for me. This is not an aryl carbon. This is an alkenol.
It's alkenol carbon.
Alkenol. Because it's not benzene. It's not the aromatic ring. Yep. Benzene can be represented as phenyl, pH. And I wrote that up here, phenyl group. And so we can abbreviate it as pH. I don't really expect any of you to do this. Sorry, I do expect you guys to do this a lot because it is a lot simpler to draw it, especially if the benzene ring is not doing something in the reaction. Remember that we can abbreviate aldehydes as CHO. But you can also abbreviate that aromatic ring with the Greek letter phi because it looks like a circle. I don't necessarily recommend it. It's one of the most confusing ways, but an organic chemist that does a lot with benzene, I guess, might shorthand their structures that way. Oops.
Series by CHO.
One more time.
By CHO.
Yeah, by CHO would be a silly way to write it. It doesn't look like it's saying anything, to be honest. Okay, so here's a cool example of this. This compound has a ketone that is both attached to an aryl carbon, so it can be called an aryl ketone or a benzylic ketone because it's at this benzylic carbon. But it's also attached to a benzylic carbon. So this ketone is called benzyl phenyl ketone. This part on the left, this part on the right is benzyl because it includes the benzylic carbon. And this part on the left is phenyl because it's just the aromatic ring. And if you're keeping track of carbons, benzyl is 6 plus the carbon off the ring. Phenyl is just 6, which means that ketone is actually speaking for a carbon itself. 7 carbons, 6 carbons, and 1 carbon from ketone.
And you don't number it the same other way.
You don't need to number it because you're saying, I have a ketone, a carbon, that has phenyl and benzyl connected. It's like you can call acetone 2-propanone. Prop has the number of carbons in it. Or you can call it dimethyl ketone. Methyl ketone 3. Yeah.
I might be getting these two things confused, but is phenyl and aryl the same? circled in orange and green?
Kind of. I should have color coded better, huh? This green thing that I circled over here, I should have circled in red because that's the benzylic group. And then this thing that I circled in orange, I should have circled in green. Because it is the aryl carbons that make up the phenyl group. Does that make sense? Good. The phenyl group is only aryl carbons. A benzyl group has that benzylic carbon.
Benzylic carbon being adjacent to the benzene.
That's right. And notice that learning objective 6, we're going to be doing reactions at those benzylic positions. So I want you guys to be well versed in them. All right, let's talk about some nomenclature. And let's take our time and go through some mono-substituted structures. Wow. That is what lazy looks like. Because we already did some practice with alkyl groups, I'm leaving alkyl groups off of this list. But for the sake of refreshing some other groups. Okay, I thought of another one I want to put up here.
Is benzylphenylketone IUPAC certified?
It's technically functional class nomenclature, and I do believe that IUPAC supports functional class nomenclature, but it's not systematic nomenclature. IUPAC also adopted many common names. So names that are not systematic in any way, that you would not guess, and they 100% accept them. A few of them are on here. Anybody want to give some of these a shot? I'll dictate, but I'd rather you guys come up and put some on the board. Why don't you first come, first serve? Come grab one and put its name up. There you go. Should spread them out more. about the second to the top?
First
Yeah.
one's here.
Yeah.
You think you could do the bottom one?
Maybe. I bet it'll be a lot easier than you think.
Things usually are.
Yeah. Good work, though. We'll talk about that one.
I just looked up from the third one down maybe.
Yeah.
Benzaldehyde.
Yeah.
That simplifies a couple of my thread.
You like that, or you don't like that, or what's up?
It seems like they're just doing too much.
All right, good work. You guys have any guesses that you maybe don't want to come up and actually put on the board? What do you think could be that bottom structure? What at least is a part of its name? If it's phenyl ether, you have to describe the other side. Diphenyl ether? No.
Benzene.
Methyl phenyl ether. That would be an acceptable name. What did you say, Niyara? There's many more. That's actually not one I was going to suggest. Meth oxy is another way that an ether can become a substituent. So this is methoxybenzene. But you could call it methylphenyl ether. By the way, how am I deciding whether methyl or phenyl comes first? How am I deciding whether benzyl or phenyl comes first?
Alphabet.
Alphabetical order.
Are all the names up there correct?
Not yet. Well, there's also more names. So bromobenzene, great. You could also call it phenyl bromide if you're going functional class name. Phenyl bromide makes the benzene ring a substituent of the bromide atom. It feels weird, right? Because it's not bromide, it's not an ion, but that's just how you name it. Like alkyl halide. This would be phenyl bromide. Chlorobenzene, also called phenyl chloride.
Are they like equal priority now? Like, you know how like naming other stuff, like certain things would take priority for like the ending?
We still have priorities. So like alcohol is higher priority still
Yeah.
than alkyl and halogens. And alkyl and halogens are still equal.
Okay.
Yeah.
So halogen, the ring is equal? So you could say either one?
A halogen in a ring to a halogen not in a ring wouldn't be named at the same time. For instance, if you had this ring that had a chain coming off of it, then you'd have to name the substituted ring as a substituent of the rest of it. And at that point, it would just go by. At that point, the aromatic ring as a substituent is just like any alkyl group. Yeah.
So does that mean that stuff like, if you have alkyl halides, then you have phenyl halides and benzyl halides?
No, these are aryl halides.
Let's say aryl nine.
Yeah. If they're attached to that aryl carbon, we call them an aryl halide. But yeah, I guess you could have a benzyl halide. If it's attached off of a benzylic carbon,
It's just kind of weird to say that.
yeah, it doesn't sound right. Benzylic halide maybe even makes more sounds better, but doesn't really matter. Bromobenzene, chlorobenzene, that's what I would encourage you guys to call them this semester. Phenyl alcohol works. That's another functional class name. It's naming phenyl as a substituent of the alcohol group. You can name the alcohol as a substituent, and that makes it hydroxybenzene. Or you can have the suffix alcohol put onto the name, but it doesn't. Okay, this is terrible. It can be called benzenol. I don't like that name. What is most common is actually the common name phenol. But technically you can call it benzenol. It looks wrong, doesn't it? You guys don't know, do you? You don't like the N in front of it? Oh, that's why it looks wrong. Thank you. Yeah, a little. Benzenol. So, predominantly, that compound is called phenol, which is really a shame, right? Because what does it sound like you're saying? Phenol. When you're trying to say phenol, phenol, you gotta pay attention to what shape your mouth takes when you say it.
Phenol.
Yeah, it is actually, if you know phenolphthalein, it's that same phenol.
Really?
Phenolphthalein, I believe, has a hydroxybenzene group. Yeah. Or some of you, when you were in my OCHEM 1 class, you were naming functional groups. And you had alcohols, and all I was looking for was alcohol, but they were aryl alcohols. And when you looked it up, you were told that they were called phenol groups. You can say an aryl alcohol is a phenol. That is a common name. It's funny though, when you have a phenol, like a dihydroxybenzene, it's called catechol, which I don't know where that came from, and I'm not going to ask you to know it. Okay, nitrobenzene, that's the only name for it, nitrobenzene. No one gave us this, but do you know what that functional group is up there? It is a sulfonal, which is similar to a sulfate, but sulfate is what this would be if it was deprotonated. No, that would be a sulfonate, actually. Sulfate is just SO4 2-. This is sulfonal, and so it becomes sulfonal benzene. We are going to learn how to make every single one of these compounds this semester, if not directly from benzene in a couple of steps, including sulfonal benzene. Aminobenzene, great. It also has a common name, which is aniline. Not to be confused with the amino acid alanine, which I often accidentally mistake it for. This is aniline. Those of you in lab already did an experiment, the synthesis of methyl orange, where you used dimethyl aniline as one of your reagents. Instead of NH2, it's NCH32. This is aniline. This one is most often called benzaldehyde. Oops, no E at the end there.
I was thinking like benzenal.
So I think that you could, similar to how we call this phenol or benzenol, I think you probably could call it. In fact, I'll look up PubChem, which is operated by the NIH. I'll look it up on there and see if they have an alternative name that it accepts. Benzenal is by far the most common version of that name. However, there is another way that you can call it. I don't necessarily recommend it. No, it doesn't look like they have benzenal on there. What they also offer is phenyl methanal. That is to say that it's a 1-carbon aldehyde, methanal, with a phenyl substituent. They also give you, and this is the one that I was going to say, but I don't necessarily recommend it, so I'm going to put it in a different color. They call it benzene carbaldehyde. And why do I not like that? What the heck is a carbaldehyde? Also, benzene carbonyl and benzoic aldehyde and benzene carboxaldehyde. Oh, actually, I'm sorry. I did say it wrong. It's not carbaldehyde. It is carboxaldehyde. No, it's still terrible. It's still not as good as benzaldehyde, in my opinion. Also, benzenaldehyde. Anyways, not names that I necessarily recommend.
Are there non-carbon aldehydes?
No.
Nitraldehyde?
No. All right, now this next one, I wouldn't call it carboxybenzene. And I get what you're going for there. But you'll notice that actually when the aldehyde is named as a substituent, it's not. The benzene is named as a substituent of a carboxaldehyde. And so this name can also flip. And the version I wouldn't recommend is that you can call it benzene carboxylic acid. But the name that I do recommend you know is benzoic acid. I think in a similar way, though, you could call it phenylmethanoic acid. I don't know, actually. They seem like they can do whatever they want. There's a common name for this group, methoxybenzene. It's not one that I necessarily will ask you guys to know because I don't generally like common names, but this has the common name anisole. All right, why don't we take a quick break? I want you guys to get up and move around, get your blood flowing a little bit, and then we're going to look at dye-substituted nomenclature.
You don't like common names, John?
Common names have a time and place, but generally, I think the best time and place is nowhere near my classroom. Yeah.
More carbon here. Now it would be shorter to label these two this way. This one would have a higher level.
You're right.
How big?
Prioritize the alkenes.
Okay.
Yep.
So you would do this.
I would number from the top counterclockwise, from the right counterclockwise. That's right. But now it's cyclooctadiene. You added in 2 extra carbons. Christina, I saw your question about pre-lab quiz, by the way, or pre-reading quiz, but I didn't have a chance to look at it and also grade everything.
Yeah, no worries.
But you're probably right
What?
that question just doesn't make any sense.
I'm so confused.
Like, what do you think you were supposed to get out of that?
I don't really understand what it was asking.
Sure.
I don't know. But then I just assumed I was wrong because I'm kind of shaky on the stuff. So I was like, I guess I just have a fundamental misunderstanding.
You know what? That's because it's the wrong answer.
That would explain.
Yeah.
I spent like an hour trying to read textbook, looking it up, and
The correct answer. What do you think the correct answer should have been?
I don't remember what the options were.
Oh, let me read them to you.
Oh, okay.
The electrons are highly reactive. The electrons are strongly stabilized. The electrons are never found on those 2 atoms. The electrons are repelled by these 2 atoms and spent little time by them.
I thought either never found or that one. Because I know on a node, that's where electrons have a probability of zero.
Just 0. A node is where they have 0 probability.
So is that the right answer?
Yeah.
Okay, great. Well, that's over the first time.
Isn't that terrible? Just a heads up. Sorry, if you took the 15 pre-reading quiz, I might have just reduced your score, which should help draw your attention to a question that was marked incorrectly, which hopefully will make it make more sense.
Yay.
Thank you, Christina. Sorry that you have to go take it again. At least you have unlimited attempts.
So I was thinking they could do Zoom for my physics class at the same time, but it's not going to work out. So I think I'll probably just have to stick and watch the remainder of the lecture on the video.
All right.
Yeah, unless you have like, do you stream a Zoom from your phone?
No, because I use an app. I use an app called Kaltura, and it takes good quality videos. It actually takes better quality videos than Zoom.
That's good.
So,
I think I'll stick to watching the videos then.
okay.
We shall see
All right. Good to see you, Jamie. Hey, were you thinking of applying to the STEM Center here, by the way?
Yeah, I looked at some stuff, but they don't have any like openings.
You should just.
I could check the wrong spot.
You should reach out to somebody. If anybody, Johnny Pope is a good person. He was just in here saying he's the only chemistry tutor scheduled on Fridays, and he is always busy. So, email Johnny Pope. I can get you his number or his email if you need it, and see who he thinks you should contact to get a support.
Okay.
All right.
I think so.
See you, Jamie.
Yeah,
yeah.
So
Thank you.
for B's, it's SP2, is that because of the double bond? Sorry, two. I'm forgetting the word dots.
Yeah.
Create an SP2 up here. This already.
So what would be the options for the oxygen?
For the oxygen.
It has a pi bond.
Yeah.
It cannot be sp2.
So I don't
Either
know.
be sp2 or sp.
I thought you were overlapping. I don't know if my grades.
It is tough,
And he was
right?
like, the way it was
No.
There is
written.
another question actually that
I
says
guarantee you
what
they
is
weren't
the
good.
carbon-carbon
And I
cycle?
did tell I was great. We did want to say it.
Good.
But I know that's what our
Good.
So because this, there's no way that's
I'm
SP2.
sure this
SP2.
Yeah.
But it has to be that this one's SP2.
No, I'm like,
So
Correct.
just process
bad.
it.
No,
And then that one is.
I agree.
Yeah, what happened? You
So the first
because
time I
this
went
one
through,
there
this
is
makes
another
sense
one
to
that
me.
asks about the flavor.
It is. That's the one I got the second time. But for this one, the one thing that actually threw me off the first time is the fact that this H2 is right next to the 2. I thought this 2 was denoting carbon. I didn't see the second 2. So I was like, oh, it's just C. Okay.
Oh.
And that kind of threw me off a little bit. But I should have guessed your charge would have made sense. Like you would have actually been a charge out. And
Yeah.
then everything else was. And this one's just due to instability.
That's right. It goes for the most substituted spot. Yeah.
And then you
And
grades, for example, I would base my like 1 3 for 3 or 2, and then it would be like whatever 200 tests. I grade like I don't know 80. You know what I mean? We divide them.
That's right. That's right. 4.
So that one you said I got this on the
Literally
very
all of
first
his
one.
answers.
Orbitals are a space that like this makes sense to know, right? But
Yeah.
that's what I just
Honestly,
and then this one we just figured out the aromatic is not all the way around. So it's an aromatic ring. It is a ring.
Which is why one of the questions I like this because
Wow.
it points out to you what's
Wow.
Okay, which that was my next one. Okay. You realize you draw
You know,
these are all drawn on chairs, right?
Manage the feelings.
Like I mean around the chair confirmation, but every time there's a chair confirmation, you draw like your these like the these swap to a chair, which is a bit
these cannot be shared. These are flat.
These are flat, but what I want to show is the way you draw
Yeah.
your pieces. You draw them like they would be on a chair.
Really?
Does that make sense?
No, this is how I draw my chairs.
They have people writing for them. Well, yeah, exactly.
Yeah.
Whereas like comedians and stuff, especially,
So
the volume
for the
I see. Yeah.
Because you've been drawing them since like I've never seen anything told us how fast like these are
I know. I was trying to say.
Oh.
and I'm like he's drawing partial flavors.
I can tell you how you see the chair in them. I'm not even trying to draw a chair. I would say it looks very different from what my actual chair. What But you're right that I do squish it.
Which makes me laugh because I chairs are one of the things that I get on this spectrum.
Yeah,
I
well,
need
you
a
might-
projection for life, but
you don't have to
chairs.
do anything. Game this class is fair. That's the only question.
I think you're right.
Never got it. Always
Yeah, I was like, oh, wait, duh.
But unfortunately, the way the carboxylic acid are almost always dead in that region. It's really hard to tell if you have a version of just OH carboxylic acid or also SPH and SPH. Ideally, they should sell so that more total light of that frequency is. So it looks like the peak of the CH plus the peak of the CH. IR is one of those like, I always choose experimental IR, and because of that, none of them, they don't always look pretty, so I go for the ones that look pretty. Actually, there's an IR NMR assignment. It's a bonus assignment that is required. But you're the only time you're going to see IR and NMR on my exams are in the bonus points. I don't actually put their spectra. I ask questions about IR and NMR in the multiple choice questions. But that's right. It's always just bonus. So I think it's a good skill to have. And no questions on part B? Great.
When's the NMR training? Is that Thursday night?
Thursday, I know there is training, but I think there's supposed to be training Friday because that's what I have in my calendar. So unless Raj was trying to cancel it, it wasn't made clear. All right, are you guys ready? Yeah, supposedly Friday morning. All right. As we learned, we do not have to prioritize the placement of the double bonds when you have polysubstituted benzenes. But as it turns out, disubstituted benzenes get their own unique nomenclature in IUPAC nomenclature. If you have a 1,2 disubstituted group, you can call this orthosubstituted. Like orthodontic. I don't know, I'm sorry, just kidding. I don't know if those are connected. But if somebody wants to find out, I've never...
I looked it up and apparently the words don't directly translate to how we use them in chemistry.
Oh, so they're not...
They are Greek words, but it's not.
They're connected, but they're not related to how we use it.
Yeah, it's not.
Ortho means straight.
Is that what orthodontics comes from?
Straight as teeth.
Yeah. Oh, interesting. A 1,3 relationship is called meta, which I don't think is related to like metacognition or meta, the meme. What? Yeah, it's not Facebook parent company. But you can abbreviate that with M. And then the only other way to arrange two substituents is 1,4, and we call this para. P. And the reason that I'm giving you ortho O, meta M, para P is because you can use either one. You can use 1,2, ortho, or O. If you are to use 1,2, you typically still put those locant positions in front of each substituent, which means that if you have a substituent of higher priority, like a hydroxy group, then you prioritize that placement. So it's easier to literally just put O, because then you can just name the substituents alphabetically, and you don't have to say this substituent goes here, right? Or if you have bromomethyl, you have to say 1-bromo-2-methyl, because it doesn't matter which one is 1 and which one is 2. And when it doesn't matter, you give the lower locant to the first alphabetically. So it's just easier to say ortho-bromomethyl, so you don't have to arrange those locants. So let's do some application of these. Can I add one more down? Oh, no, just kidding. Maybe. Yeah, maybe I will. Does anyone feel brave enough to give me the name of one of these compounds? I'll write it up here for you.
Orthophenol.
Well, you need to describe that there are two. So we can say ortho.
Would it be mono orthophenol?
No. We can't use phenol anymore because it's not that mono-substituted. So you can call it orthohydroxyphenol. Or you could call it orthodihydroxybenzene.
Doesn't ortho mean di?
No, it means 1, 2. Good question.
Oh, because you can have two separate things.
Absolutely, like the one above it. So orthodihydroxybenzene or orthohydroxyphenol. One of those alcohols is phenol. One of them is hydroxy. Does it matter which? No. Another one?
The first one is ortho-methyl-nitrobenzene.
LMN. I think you said nitro. Methyl nitro?
Methyl nitro.
Oh yeah. Okay. Sorry. Not calling you crazy. I'm crazy. Ortho methyl nitro benzene. Another one?
Top one, meta-bromochlorobenzene.
Good. Meta-bromochlorobenzene. Good. Para. hydroxysulfonyl benzene. You could also call it not parahydroxysulfonyl phenol. Parasulfonyl phenol. Phenol already implies the OH group. Good. Nayira, did you want to give me one? Did I see your hand raised?
It was one of those, but I can try the bottom one.
Sure. The bottom one is a trick, by the way. So if you know it, I have told you it in OChem 1, but it is a trick. You can give it a shot if you want.
Meta. Chloro.
Off to a good start. What's your gut telling you? If I didn't tell you it was a trick, what were you going to say?
It's metacarboxylic acid.
Right, and that's what you were leaning towards, right?
Yes.
You were going to call it metachlorobenzoic acid. It's not a carboxylic acid. It's not benzoic acid. It's actually a benzoic acid with an extra oxygen, specifically in an OO single bond. Do you know what functional group has an OO single bond? I think you know from your compound over the summer.
Yes, an ester.
Not an ester. You had that big ring that had the group that came up over it, right? It was 2 O's, and I made you name it. And there's a really small molecule that also has the functional group name in it, except the 2 O's are bonded also to hydrogens. Peroxide. So this is a peroxybenzoic acid. This is metachloroperoxybenzoic acid, also known as
Peroxybenzoic acid?
no,
Perzoic acid?
no, metachloroperoxybenzoic acid. That gave me goosebumps. You are also excited. Isn't it cool? You figured it out. Now you know what the heck that jumble of letters means. That's what it is.
What does it do?
It's our. Anybody want to say?
What does it give?
What do we use it for? Epoxidation.
Wow.
This reacts with alkenes to give epoxides. Great.
Does it form benzoic acid?
Yeah, the byproduct is benzoic acid. The byproduct is MCBA, metachlorobenzoic acid.
That one goes away.
No, this one.
Really?
That one goes away.
So does the hydrogen just...
And the hydrogen actually comes over here, and the double bond goes over here. It's a very fun mechanism. I didn't test you on it because it just doesn't mean anything. But I love it. It's such a cool shape. I'll show it to you at the end of class. Last one. Come on. We got this. Good. Meta-amino-benzaldehyde. Here's the deal. I can't call it both aniline and benzaldehyde. And it's really hard to call an aldehyde or a carboxylic acid as a suffix, or excuse me, as a substituent. So it's really challenging to name this meta-carbaldehyde aniline. I don't think anybody would call it that. I'm not sure IUPAC would accept it. So I do want you guys to look at this list and notice these two compounds which are basically always given as suffixes, never given as prefixes, never substituents. So you can call some amino compounds aniline, but you can't call all amino compounds aniline if that's connected with a compound with benzoic acid or benzaldehyde. You guys in OChem 2 lab, you'll be doing a synthesis project towards the end of the semester. One of the options is to take a compound called PABA, which is para-amino-benzoic acid. Again, can't be called aniline because how would you name the carboxylic acid as a substituent? You can't. That carboxylic acid has to be in the root of the name. Does that make sense? We had this option before where we could call it orthohydroxyphenol or orthodihydroxybenzene, which I guess I never actually finished writing the word benzene. Interchangeable. And really any other time I have an NH2 group, interchangeably I can call it amino or aniline, but not if it's one of these two. Never substituents. So I would give these priority in naming. So what's the only other thing we need to name with benzene? Yeah, anything that goes beyond disubstitution. You guys all good with that side if I cover it? So I'm going to put a structure up. And now, based on all of the learning you've done today, I want you to see what you think would be an acceptable name for it. Some of you know this compound because you've chosen it. You know its common name or its prescribed name? Propofol, used as an anesthetic? Anesthetic in vet science?
In medicine, period.
Really?
Yeah.
Oh, I didn't know it was given to humans.
Exact same drug.
Okay. Propofol, which might tell you there are propyl groups and an alcohol, but how does it tell you there's a benzene ring? It doesn't. How might you name this, given what you've learned about monosubstituted benzenes and their common names and disubstituted benzenes?
1,3-diisopropyl-phenol.
1,3-diisopropyl-phenol. When you call this molecule phenol, you are agreeing to call the alcohol carbon carbon 1. That's one of our assumptions. So if you use a common name, that group is on carbon 1. What would you call it now?
1,6.
Good. 1,6.
2,6.
Oh, you're right. Thank you. 2,6-diisopropyl phenol. Maybe you can hear the phenol in there by propofol, but it's not clear, right? How else might you try to name it?
Could you say it like a meta-isopropyl phenol?
We'd have to say meta-diisopropyl phenol, because the relationship between the two isopropyl groups is that they are meta to each other, right? We can't. So rule number 2 here with, and sorry, I didn't really title this. We're not just looking at tri-substituted, we're looking at 3, 4, 5, and 6. Poly-substituted. The common name must mean that that group is at carbon number 1, and ortho, meta, para are not allowed. Not my rule. Although I think you can see how it might be confusing. Should I have called it ortho diisopropyl phenol because the isopropyl groups are ortho to the phenol? And if it is meta diisopropyl phenol, are the groups meta to each other here, or are they meta to each other here, right? So ortho, meta, para, they do a good enough job describing the relationship of two groups. That's it. When there are more than two groups, it becomes too confusing which two groups are being described. Can you give me another way to name this structure that doesn't use the common name, phenol?
2,6-diisopropyl hydroxybenzene.
You'll have to name where hydroxy is.
1-hydroxybenzene.
So you want to call it 1, 2, and then all the way to 6, right? Yeah, I agree. 2,6-dihydroxy, 2,6-diisopropyl. Does H come before I? A, B, C, D, E, H, I. So hydroxy actually comes first. So 1-hydroxy, 2,6-diisopropyl benzene. Good. All right, let's do another one. You know, IUPAC does get cluttered and confusing sometimes, and so I'm never going to give you structures that I look at and think that name is probably too convoluted. However, it is useful to understand how to prioritize a lot of these. I think technically the amine group is higher priority than the bromine group, but I don't know how well that's enforced. So I came up with this example because I wanted to show that it would be numbered differently depending on whether you use the common name or not. But I don't know if it is a good example for that after all. So what would be the name for the common name? Good. I told you, or maybe that's because I told you. 3,4-dibromoaniline. And now I'm nervous to put the other name on there because this is going on the internet, and I don't want people to be like, he doesn't know the amine group is higher priority. I think that this compound would be 4-amino 1,2-dibromobenzene. We're gonna get the lowest possible locant set.
So in this, it's the set, not the first.
That's correct. It's never about the first number. It's about the set. Earlier, it was about the set as well, not about the first number, because the first number was for the alkene. the alkene was always going to be, well, I guess that's not the first. That was later in the name. The set is either 1, 3, 4, or the set is 1, 2, 4. 2 is lower than 3, so we prioritize that. So here's what I want you guys to do. I'm going to look into this. Using these groups, I want you to draw a structure and then swap it with somebody else and see if you can name their structure. Just take 1 minute. Pick 2 to 4 of these, or 2 to 6. Pick 2 to 6 of these and put them onto a benzene ring. And we'll go from there. You have to do it. You gotta, or I will drop you. I'm just kidding. I know, I told you. It's not my fault. What? Oh, you can call aniline benzenamine. Good stuff. Yeah. You don't want to do that? Come on.
Amine or imine?
Amine.
What's the word for epoxide?
I don't know. Epoxy.
Damn. Well, I was seriously gonna do that with another OH, and then I was like, no, that's all OH. Hell yeah, that'll fuck you up.
That's called super alcohol.
No, that's right.
What would I call it? I don't know.
Matt, you guys are done. You want to exchange? Axel, did you get to exchange yet? Killian, you want to exchange with Axel?
Well, I can keep the hex up.
Thank you.
If we got the.
Boring.
Oh my god.
What?
Oh wait, okay.
You know, to be fair, I actually said 6 of them, but not one of them 6 times.
But you did not say that.
Right. What am I going to do?
Here, I'll change. What if I change my
I'm not giving you participation points for today. Actually, I did take your participation points.
I changed one. So. Me too. Wait, what is orange? What you had a piece of that? My little rat
Oh yeah, I did forget some. I always forget some.
Yeah, let me just draw yours real quick so I don't forget.
I'm gonna make some space here on my examples.
Dude. You should have changed it. Yeah, too late. I can just make that.
What comes first in priority, alcohol or carboxylic?
Carboxylic acid. Especially since you basically have to name it benzoic acid.
Oh, okay, yeah, that's okay.
All right. I came up with an example, by the way, that works the way I wanted it to before. If I call the amine group aniline, then my 2 alcohols can be at 3,4-dihydroxyaniline. But I have to prioritize alcohol over amines, so otherwise I can call it 4-amino 1,3-dihydroxybenzene. If I'm not calling that amino in aniline. That's what I was trying to get at earlier with this example, but I don't think it would work. I looked it up and nobody reports this as 4-amino 1,2-dibromobenzene. So it was a bad example. A couple of other ones I actually wanted to point out. I did forget them. This guy right here is called vinyl benzene. It's a good reminder because this is a vinyl group. A 2-carbon alkene is called vinyl, as opposed to a 3-carbon group, which is called allyl benzene. But vinyl benzene has a common name, one that I don't really expect you to know. The precursor to polystyrene, also colloquially known as styrofoam. Exactly. Thank you. And something I wanted to show you guys. There is another class that's very common, and that's the xylene family. Z-Y-L-E-N-E. The xylenes are families of dimethyls. So you have orthoxylene, metaxylene, and paraxylene. And they're good examples of how benzene hydrogens change their NMR signals based on positions of substitution, but beyond that, we're not going to use those compounds very much. These are other arenes, biphenyl, when 2 aromatic rings are linked by a sigma bond, biphenyl. Stilbene, when there's this alkene, otherwise called 1,2-diphenyl ethene. Down on the bottom left is naphthalene. It's fused, 2 rings together. Anthracene, 3 rings fused together. Phenanthrene, 3 rings fused. Oh, phenanthrene's not up there. Phenanthrene is 3 rings fused together, except one of them is offset, like this. You guys should recognize phenanthrene from our course homepage. This is cyclotriphenanthrene, where 3 phenanthrene rings that have been substituted with amino groups are cyclized. There are systematic ways to number the positions on naphthalene, anthracene, phenanthrene. I think the other one that was up there was naphthalene or something weird. We're not going to get into them. We're not going to look at their reactions very much. Naphthacene. But if you can imagine extending these aromatic rings and fusing them together, it probably exists. There are big, big molecules. There's another one, but it's escaping me. So if I think of it before next class, I'll pull it up. Next class, we're going to look at aromaticity and why we call it the aromatic ring and what other compounds are aromatic despite benzene being the aromatic ring. No. Have a good night, guys.